Hello, friends. So recently we've been looking at a variety of, yesterday you saw some applications of exponential and logarithmic functions and how we can use logs to solve different applications. Things that you've seen in the past would include like compound interest, your continuously compounded interest, which was base E, things like half-life, radioactive decay. You've seen this before in chemistry and physics. I'm also going to point out that logarithms play a key role back in chemistry when you talk about pH. Other things recently, maybe if you've been following the coronavirus, you talk about a logarithmic scale and you see graphs that are horizontally, the x-axis would be based in time, which would be linear, but then vertically you'd have a logarithmic scale, which shows a percentage of increase over time. Now, typically that is base 10, so base 10 we get into, or base 100 even, so that we have a logarithmic growth. If it's base 100, it's a percentage of change, because base 100 would give us a percentage. Now, some other things that might happen along the way is going. Hold on, phone call. Hello? Oh, really? You're gonna send it over? Okay, let me pull it up. Just a moment now. Yeah, we were kind of in the middle of working through a few things. Okay, hold on. Yeah, we can take care of it. Wasn't in the plans, but okay. Yeah, 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 yeah. I think we can handle it. Yeah. Okay. Okay. Uh-huh. Yeah, yeah, yeah. I know. I I know. We got this. We can do this. I'll explain it, and then we'll take it away, and then we'll go from there. All right. Thanks. Bye. What do you know? Sorry about that, but we just got a phone call. The forensics lab has just sent over a bit of information for us. So actually, here goes. There was kind of a thing that happened around here. I don't know if it was in the news just the other day. Let me switch over to what they just sent. So apparently, 6 people were recently found deceased, all in the same room the other morning at 11 a.m. And actually, they just called up saying, "Hey, we're forensic analysis. What's going to happen is actually if you have something cooling in a room or warming up in a room, it actually follows exponential growth, exponential decay." Explain that something's called Newton's law of cooling. Newton's law of cooling is this property that if you have something of a specific temperature sitting out, it cools exponentially according to this model here. So what the forensics lab just did, they sent us over all the information about the victims at this residence. Now, reading through things, the crew took body temperatures when they found the bodies, and again at 11:30, and they noticed that they're decreasing in temperature over time. So here's all the information that we have. Oh no! It's believed that the 6 people may have been members of a cult, and that the last person to die was the leader of the cult. Find the time of death. Oh no! So we've been tasked. Pulling this back together. Guess we've got a job to do. We've been tasked that we need to find the time of deaths for these 6 individual people, place them in order, and ultimately, who died last? Who is actually the leader of this cult? So, I'm going to go back to the information that's been provided to us. Let's see, we've got Newton's law of cooling as an exponential function following this rule. Let's see, we have U of t. It's our function notation. That's the current temperature of the object. Well, U of t would be the temperature after time t. Big T is our ambient temperature, the surrounding area. So ambient temperature, that would be like your room temperature if you have a hot cup of coffee just sitting out. U sub 0, that's the original temperature. So the temperature at, time 0, which would make sense. Time 0 temperature, temperature after some time has passed. K is some constant. Oh, that's like in our compound interest, or our rate of change. We saw that with half-life. And okay, little t is how much time has passed. All right, so we've got 6 different people. Looks like their names are R, be a pirate. You got to do that right. R, be a pirate. Not to make fun of somebody, but Latoya Linear, Milt, Multiplier, Tony Tangent, Polynomial. Gotta hate those polynomials. And Lewis Logarithm. Wonder if he goes by Lou by short or Low. Logarithm. I think I'll call him Lou. Logarithm. Anyways, we've got to find the time of deaths for these 6 individuals. Let's take a look at how we can apply Newton's law of cooling to determine time passed. I'm going to take this information, I'm going to pull it over to a Word document here. There we go. So we know that cooling bodies obey Newton's law of cooling. It cools or heats. I imagine this works just the same as if you were heating something up in the oven. Defrosting something coming out of the freezer. You've got some ambient temperature. Now, if you're cooking something in an oven, it would be the temperature of the oven. You've got the initial temperature, you've got the final temperature, some rate of change, K, some constant of change that is dependent on each individual body. So, my hot cup of tea is going to have a different K value than my ice cream sitting on the counter melting out there. Let's see. So, taking some information. R, be a pirate. Gonna close this so I don't burn through things. So RB here, this temperature dropped from 85.9 degrees to 82.3 degrees from 11 o'clock to 11:30. Okay, first we need to find some constant value K. So that's the rate of change. Now the things that we know, we've got an initial temperature. We've got a final temperature. We've got how much time has passed. So 30 minutes has passed. And we also know that our ambient temperature, our room temperature, is about 70 degrees. So I'll put that information there. We've got our starting temperature. We've got our final temperature using our function notation 30 minutes later. We've got the time that's passed is 30 minutes, and our ambient, our surrounding temperature, room temperature, is 70 degrees. Do you believe it said that somewhere in there? Yep, it's in there. Room temperature, 70 degrees. Well, we've got Newton's law of cooling. Oh no, did I just screw everything up? There we go. We've got Newton's law of cooling right there. I can put all that information in there. Now I suppose I'm just going to go through and work through the math, not simplifying along the way. I'll get everything into the calculator later on. Now, solving, there's our variable k up in the exponent there. So we know that when we've got an exponent that's a variable, we're going to need a log eventually. Let's see, order of operations, this is multiplication inside parentheses. Here, this is an outermost piece. I'm going to subtract that 70 degrees. Well, trying to isolate the k, I'm going to divide by what we're multiplying out here. Now at this point, I can plop this division into my calculator. I'm just going to leave it as is so we can see where the pieces come from, but we've got exponential base e. We need to cancel that. That's going to be log base e, or natural log. So I'm going to take the natural log of both sides. Now I can simplify this in my calculator. This is some number in the calculator, but I'm going to leave it for right now. On the right side, we've got natural log of exponential base e. So log base e of exponent base e, those are inverses. Those just cancel out. We'll be left with k times 30. And well, if I want k by itself, I'm going to have to divide by 30. All right, I'm going to go over to my calculator. We'll plop this in there. Now there's the ln button next to the 4. That is natural log. So I'm going to do ln. Well, 82.3 minus 70. That's 12.3 divided by 85.9 minus 70. That's 15.9. And then we're going to divide that by 30. All right, so we get negative 0.008557. Now that k, that's a constant rate of change. That's really like a percentage of change. So it's negative. Our difference in temperatures is decreasing. The difference in the temperature of the body to room temperature is decreasing over time at a percentage. Okay, so going back, All right, we've got K is about that. That's what we were asked to do first for Arby. Next up, well, part B, we also know that Arby's temperature decreased from 98 degrees to 85.9 degrees after some amount of time t. We know his constant of cooling is K. Well, we don't know the last time that Arby was at 98 degrees. So we need to figure out how much time passed from 98 to reach 85.9. So thinking about all the information that we have, we've got K, we've got our final temperature. This was the temperature, 85.9 degrees at 11 o'clock. 98 degrees was Arby's original temperature. So if we can figure out how much time passed from 98 degrees to cool down to 85.9, we can figure out how much time passed from when Arby went away until 11 o'clock. Our room temperature is 70 degrees, and our time, we don't know that. So we've got Newton's law of cooling. I'm going to take that above information, plug it in. All right, so we've got temperature after some amount of time has passed. We've got our ambient, our surrounding, our room temperature. We've got Arby's normal temperature, 70 degrees again. We know K this time. We're trying to solve for T. So it's very similar. We just need to plug our way through, solve for T. So I'm going to subtract that 70. I've got this multiplication. I'm going to divide. We've got exponential base E, the natural number. I'm going to take the natural log of both sides. All right. Oh, that shouldn't be a 30 in there. That should be, I'm just going to cover that up right now. That's a T. Oh, ln of E, those are inverses. They cancel. See, there's the T again. And we want to solve T, so we're going to divide. We can get T. Now, of course, you could plop all this into your calculator, find some values along the way. I'm holding on to it just so I can use the calculator as exact, as precise as possible. So we want T. I'm going to go back to the calculator, plug this in. We have natural log of 85.9 minus 70 is 15.9 degrees. Divided by 98 minus 70, that's 28 degrees. And we're going to divide by that negative 0.008557. Now in the calculator, I'm just going to copy that down. All right, that gives us 66.128. So, well, that's time, 66 minutes. So it's 66 minutes before 11 a.m. So that's telling us from the last time Arby was 98 degrees, 66 minutes has passed until it was 85.9, the temperature at 11 o'clock. So 66 minutes before 11 a.m. That is Arby. That's not right. That's only 6 minutes. Arby, sadly, went away at 9:54 a.m. Now, what we've got to do, we've gone through Arby. It's up to you. You've got to figure out the time of demise for each of our 6 additional people. You're going to use the temperature at 11 o'clock, the temperature at 11:30, because that's a known time. You're going to use those to find K. Then you're going to use K that you just found with the normal temperature and the temperature at 11 to figure out how much time passed from the normal temperature to arrive at 11 o'clock. Work backwards, figure out the time that has passed, put those candidates in order. What's the order? We have the last person to die is the leader of our cult. Who was the cult leader? I've got faith in you. The forensics team has faith in you. Good luck. Let me know if you need anything.